Yay!
Yay! Let's look at what happens to a current loop in a magnetic field. What is going to happen is that you're going to get a torque on the loop and it's going to spin. And this is the fundamental idea behind electric motors. So let's see what happens. Let's see what how much energy we get out of this kind of a thing. Let's look at this loop in particular. So suppose we got a magnetic field going to the right, and then I put the loop in the magnetic field so that the plane of the loop is parallel to the field. So the magnetic moment, mu, and remember mu, the magnetic moment is just I times a vector, the area vector, coming off of this thing, perpendicular to the plane of the loop. So this magnetic moment, in that case, is just pointed up. And the shortcut for that is that you turn your right hand, your fingers in the direction that the current is going around the loop, and then your thumb points in the direction of the magnetic moment is the shorthand. So suppose we have something like this. What's going to happen is that loop is going to twist in the magnetic field. Why? Because we can look at the forces on those individual legs. We don't have to worry about this leg or that leg, because look, the current is going parallel to the magnetic field, right? And remember what the relationship is. It's that the magnetic force is I, L cross B. So if L and B are in the same direction or opposite directions, parallel or anti-parallel, then the cross product is 0, so we don't have to worry about it. So this is ILB sine theta, where theta is the angle between the direction of the current and the magnetic field. Here, for that particular orientation, that's going to be 90 degrees, right? So let's look at this leg over here. What about the one here on the left? What's the force on that one? That's just going to be, if you do your right-hand rule, you put your thumb in the direction of that current. That's going to be minus y. And then the direction of the magnetic field is in the x direction. So I want to know you could just do the right-hand rule with your fingers, but you can also do it this way, sort of procedurally. So what is minus y cross x? This is our, here it's our coordinate system, the usual one that we set up. Well, how do I find that out? Again, you can either use the right-hand rule, or sometimes I just like to do this. X to Y to Z and back to X. As you go around the circle, you get positive cross products. So X hat, if you go around the circle this way, X hat cross Y hat is Z hat. Z hat cross X hat is Y hat, right? Remember that shortcut from Physics 1. We're going the other way. So we're going Y cross X. So that's going to be Z, but we're going the wrong way, so it's a minus Z. But then there's a minus Y, right? So what you get out of that is Z hat. So the direction of the force on that segment is going to be up. There's the magnetic force. And the other one, since it's pointed the other direction, we're just going to get a negative. You can go through that again and satisfy yourself that you get that direction. So on one side, we get a force going up. On the other side, we get a force going down. So what that's going to do is it's going to exert a torque, right? It's going to make that thing spin. So the center of mass of the thing isn't going to move, but it's going to spin. And then how do we figure out the torque? Let's suppose that this is W and L. It's like a rectangular loop, right? So what is the magnitude of the torque? The magnitude of the torque is just going to be the force times that, what do you call it in engineering, like lever arm. Yep. So anyway, it's the distance to the axis of rotation. There's our axis of rotation. So the distance is W over 2. So it's just going to be the force times W over 2. And both of those forces are doing the same torque, right? It's making it rotate in the same direction. So I have to add them together. So I get twice that amount of torque. So this is just going to be, the 2's of course cancel. So it's just going to be the force is ILB. The sine of theta is just 1 ILB W. But look, L times W, that's just the area of the loop. That's just IAB. And IA is just our magnetic moment. That's just the magnitude of the magnetic moment. So it's just mu times B. Now, in general, that's going to be mu B sine theta. The torque is going to be mu B sine theta. And the way that we usually write that is mu cross B, right? If those are vectors, then the magnitude of it would be mu B sine theta. So the torque is just the cross product of mu and B. So what's going to happen is, as I rotate this thing over, imagine starting it off in this situation, and then it rotates through here, and then eventually it goes to here. Like whenever you see something like a mu cross a B, what that means is what they really want to have happen is this thing wants to twist until mu and B are in the same direction. So the final state over here is that you have mu and B in the same direction. That's really what the loop wants to do. It wants to align its magnetic field with the overall, the sort of external magnetic field. Because remember, mu is the direction of the magnetic field that the loop generates, because it's a little loop of current. So what nature really wants to do is align those two things. So that's what that mu cross B is really telling you. Let's see how much energy we get out of that. Energy, let's look at the change of potential energy that we get from our starting, which was over here, until the ending situation over there. So the change of energy, remember for rotational motion, it's sort of like, remember the change, like the work done in first semester mechanics was like the integral of force times dr, right? Force times a little bit of distance. For rotational motion, it's almost the same thing. It's rotational force times a little bit of angle, tau d theta. So we're going to do that from pi to 0, because at first the mu and the b, that theta is a pi, they're off by pi, and in the final situation they're 0, they're totally aligned. So we're going from pi to 0. Okay, so let's write it down. So this is going to be pi to 0, and this is going to be mu b sine theta d theta. Okay. Well, mu and b, those are just constants, so I just need to integrate sine theta d theta. And if you integrate sine, you get minus cosine, minus mu b, and then I'm going to have cosine theta from pi to 0. So I'm going to have to be careful, right? It's mu b. Cosine of 0 is 1. And then I'm going to have to subtract the cosine of pi, which is minus 1, minus 1, right? So hopefully I didn't lose a minus sign in there. So I get 1 minus 1 is 2. So I get minus 2 mu b. That's the change of potential energy as I go from one to the other. Does the minus sign make sense? Yes, it does, because we've lost potential energy. That potential energy, as it's losing potential, it's turned into kinetic, right? We're going from sort of an unstable situation to a stable one. So we've lost potential energy. The other way to think about it is that we can store energy in the system by rotating the thing to where it doesn't align with the magnetic field. And then when we let it go, then it aligns, right? So we can store potential energy in the system and then it gets released. So that makes sense that it's negative. And so just for kicks, let's put some numbers in there to see how this works. This is exactly how an electric motor works. Let's say, let's have easy numbers. Let's say I is 2. The area of this thing is, I don't know, 1 square meter. We'll just make up easy numbers. Let's say B is a quarter of a Tesla. So if you put those in there, just up here. So the change in potential energy, if you put that would just be a 2 times a quarter. Oh, it was just minus 1. Minus 1 joule. Well, I made that really easy, didn't I? Okay, this is how electric motors work. The only complicating factor is that the way that we have it here, once the fields align, once the thing twists until its mu aligns with the B, then it stops, right? So the genius behind electric motors is that once you make that half turn, you put a little device in there called a commutator is one way to do it that reverses the direction of the current, right? So now you're back in the original situation. And so then it twists another half turn. But then as soon as it makes that half turn, you switch the direction of the current again. And so it constantly spins. And so every half turn, you get this minus 1 joule. So for a full turn, every turn, you're going to get 2 joules out of this motor. And then you can compute the amount of work you get, the amount of energy you get out of a motor. So this is the way to fundamentally understand how the modern world works.